Hello everyone. In this video we are going to check the Nyquist stability criterion for a given system for which you can see the transfer function over here. So the controller is in the form of a proportional one and the process is given as 1 over s times s plus 1 squared. So we can say that we have L of s which is equal to GC times GP, and it's equal to K over S times 1 plus S squared. Before checking the Nyquist, drawing the Nyquist plot and then checking the Nyquist stability criterion, we can have a look at the root locus map for this system. Here you can see the positive locus. We have a pole at the origin and 2 poles at -1. And you can see the root locus would be something like this. And it's obvious that for values of k between 0 and 2, the system will be stable. For k bigger than 2, the system will become unstable. And there will be 2 unstable poles. And keep in mind that we are talking about the closed loop system. I can also show you how the negative locus will look like for this system. So it will be approximately like this. We will have one branch going towards infinity, plus infinity, and there will be 2 other branches behaving in a way like this. And you can see that for any value of k, for the negative locus, for k smaller than 0, the system will be unstable, the closed loop system, with 1 unstable pole. So for k smaller than 0, we will have an unstable system with 1 unstable pole. For k bigger than 2, we will have 2 unstable poles. And for k between 0 and 2, the system will be stable. Okay, now we are going to check this with the Nyquist plot. We will see whether we get the same results or not, and I hope that we will get exactly the same result. Alright, so to start, we'll assume that k is equal to 1. Therefore, L of s will be equal to 1 over s times 1 plus s squared. We have the transfer function for our L of s. We need to consider the contour. This is the real axis, imaginary axis, and we have our contour C like this. The poles and zeros of the system are located at the origin. One is at origin, and there are 2 at the point -1. But now our contour is passing over a pole at the origin, and we don't want this. The contour should not cross any pole of the system. Therefore, we need to modify our contour slightly. We can do this close to the origin by modifying the contour in this way, so keeping the pole outside, or we can do it in the other way by changing the contour in this way. In that way, one pole will remain inside the contour. Either way could work, so we can pick any one that we want. For now, I'll go with the option in which we have the pole outside of the contour. So I will indeed pick this contour. Okay. So just a second. Again, my PC responds with some delay, so I need I need to adjust myself to that. Alright, but anyways, we just keep the pole outside of the contour. I will draw it again over here to give you an idea of where we or how we form our contour. But again, keep in mind that both ways will work. So I picked the contour like this. Now you can see that there are no poles inside there are no poles of the open loop system inside the contour, and as a result, P will be equal to 0. If I had chosen the other option, let's say we had the open loop poles here and I had chosen the contour to be like this, in this case the P would be equal to 1. So as I said again, you can pick any of these two. Both should give you exactly the same result. But for now, let's stick to this option. So we have our contour like this. Now if I look at the contour that we have, it could be divided into a given number of segments. So we have one region over here. I can call it region number 1 maybe, for which we have S equal to j omega, and omega starts from 0 plus because it doesn't start from exactly the origin, and it goes up to plus infinity. We have a segment over here, I can call it segment number 2, for which we have S equal to j omega, and omega starts from minus infinity and it goes down to 0 minus. Alternatively, for this segment, we can also say that we have S equal to minus j omega, where omega starts from 0 plus, it goes towards plus infinity. Okay, so they are indeed equivalent to each other. Then we have the segment, the third segment over here. Indeed, we have the big semicircle, let's say. We can call it a segment number 3, for which we have S equal to R e to j theta, where R goes towards infinity and theta goes from pi over 2 to minus pi over 2 in a clockwise way. To minus pi over 2 in a clockwise way. And finally, we have this small semicircle segment here. I can call it as segment number 4. So I'm talking about this segment here. Segment number 4. For segment number 4, we can say that S is equal to R e to j theta, but where R goes towards 0, because we have a very small semicircle just to exclude the pole at the origin. So R goes towards 0, and theta goes from minus pi over 2 to pi over 2 in a counterclockwise way. So the semicircle is like this, yeah? We start from minus pi over 2 and we end at plus pi over 2. And the radius is quite small. We have 4 segments. Now we can start to think about how we draw the Nyquist plot for this system. The first one to start is starting from segment number 1 indeed. We have S equal to j omega. Omega is from 0 plus to plus infinity. Okay, now let's see how we can deal with this case. L of S will become equal to L of j omega. We will have 1 over j omega times 1 plus j omega squared. For this system, we can refer to the body plot. Body plot of the system, we have one pole at the origin, and for the body plot, we will have the amplitude plot. And a phase plot. So this is something that you should already know, yeah? How to draw the body plot for a given system. Omega equal to 1 is the corner frequency. The approximate body plot that we would have for this system will be up to omega equal to 1. We will have the effect of the pole at the origin, so minus 20 dB per decade will be the slope. And after omega equal to 1, it will become minus 60 dB per decade. This is the asymptotical amplitude plot. In terms of the phase, initially the initial phase will be equal to minus pi over 2. At omega equal to 1, we will have another minus pi over 2, so we will have minus pi at omega equal to 1. And after omega equal to 10, let's say, we will have another minus pi over 2, so minus 3 pi over 2 will be the final value. So the phase will be somehow like this. Approximately, okay? And at omega equal to 10, over here we will have, it's 1 decade after omega equal to 1, so we'll have minus 60 decibel. Now we can refer to this information and draw the part of the Nyquist plot. Yeah? At very low frequencies, we can see that the amplitude will be infinity and the phase will be equal to minus pi over 2. With the phase of minus pi over 2, we will have the amplitude of infinity. So it means that if I start to draw it here, let's say this is our S-plane for the Nyquist plot, where we have the real and imaginary axis. At S or omega equal to 0 plus, we will have the phase equal to phase of L of j omega will be equal to minus pi over 2 minus some epsilon. And you can see it over here, yeah? Because from the pole at the origin, we have the exact minus pi over 2. And from the two poles that we have at minus 1, we will have a very small negative phase injected to our system. So the phase will always be below minus pi over 2. And as a result, at very, very low frequencies, we will have minus pi over 2 minus some epsilon. In terms of the amplitude, it will go towards infinity, the amplitude, yeah? So it means that since the phase is equal to minus pi over 2 minus epsilon, we will be in the third quarter, somewhere, let's say, around here. This is what we have for omega equal to 0 plus. Then, as the value of omega increases, at some point, at around indeed omega equal to 1, the phase will go towards minus pi. So phase of minus pi will be somewhere here. And the amplitude will become 0 dB or 1. So we will kind of just a second, again my PC didn't behave as expected. So we will have something like this, where we have some amplitude which could be indeed determined exactly. it will be somewhere below or smaller than 1, because if I draw the exact indeed, the more precise body plot, if we draw it, it will be smaller than 0 dB. So therefore this will not be 1, but it will be some different value that we will determine the exact value right now. But we know that it will happen around the frequency of omega equal to 1. So now we can indeed have a look at different values for the omega as well. Let's say omega is equal to 0 plus, or it's equal to epsilon. Yeah? In terms of the amplitude, we know that it will be equal to, it will approach infinity, but we can also determine the real and imaginary parts. So amplitude of L of j omega will be equal to amplitude of 1 over j omega times 1 plus j omega squared. I can expand what we have at the denominator, so this will be equal to amplitude of, we change the size of the pen, if I can. Okay, looks like I can't. So we'll have 1 over j omega times 1 plus 2 j omega minus omega squared. And this could be written as 1 over amplitude of j omega times 1 minus omega squared minus 2 omega squared. Now if I want to separate the real and imaginary parts of this, it will be in this form. I can multiply the numerator and the denominator with j omega times 1 minus omega squared plus 2 omega squared minus omega squared minus 2 omega squared, and this will give us, as the numerator, we will have j omega times 1 minus omega squared plus 2 omega squared, and at the denominator we will have the first term squared minus the second term squared. So we'll have j omega times 1 minus omega squared minus 2 omega squared. And then we can rewrite this. We can continue to simplify it. 1 minus omega squared plus 2 omega squared. At the denominator we will have minus omega squared times minus 1 minus omega squared minus 4 omega to the power of 4. And then we can separate now the real and imaginary parts. Yeah? Let me keep it like this. If I separate the imaginary and real parts, it will be in the form of j times omega times 1 minus omega squared plus 2 omega squared over the denominator, which is, I can also take the minus sign out, omega squared times 1 minus omega squared plus 4 omega to the power of 4. And we will have minus 2 omega squared over omega squared times 1 minus omega squared plus 4 omega to the power of 4. And if I simplify it one more time, we will get this minus j times 1 minus omega squared plus 2 omega over omega times 1 minus omega squared plus 4 omega to the power of 3 minus, I just simplify this fraction as 2 over 1 minus omega squared plus 4 omega squared. So basically this is what we have for L of j omega, yeah? So L of j omega is equal to, if you remove the amplitude, is equal to this expression. So the real part of L of j omega and imaginary parts of L of j omega could be separated from each other, and we can see what happens to the real part as omega goes towards 0 and what happens to the imaginary part as omega goes towards 0 plus. For the real part we have this limit minus 2 over 1 minus omega squared plus 4 omega squared, and you can see that this will be equal to minus 2. For the imaginary part, we will have the limit as omega goes towards 0 plus minus 1 minus omega squared plus 2 omega over omega times 1 minus omega squared plus 4 omega to the power of 3, which will be infinity. So the real part will be equal to minus 2 and the imaginary part will be equal to plus infinity. Therefore, in the Nyquist plot that we have here, we can kind of say that I can indeed correct whatever I have here. If this is minus 2, we will say that at omega equal to 0 plus, let me remove whatever I had here. Okay, I'm still waiting for the system to respond. So this is something that we will not have. But now, at omega equal to 0 plus, we will have minus 2 for the real part and infinity for the imaginary part. Now we need to see what happens when we have omega equal to 1. So L of j omega when omega approaches 1. We want to see how the amplitude of the real part and imaginary part will behave, and also how the, let's say, in terms of amplitude and the phase our system will be. So if I want to find out the phase of L of j omega, phase of L of j omega will be equal to phase of numerator, which is 0, minus phase of denominator. For the denominator, we have a pole at the origin, so pi over 2 comes from that. Plus, we have 2 poles at the point minus 1, so 2 inverse tangent of omega over 1. This will be the phase that we have. So basically, we'll have minus pi over 2 minus 2 times inverse tangent of omega. This is the phase of L of j omega. And now we can easily find the phase at the different values of omega. Phase of L of j omega at omega equal to 1 will be equal to minus pi over 2 minus 2 times inverse tangent of 1. And this is equal to pi over 4. So we'll have minus pi over 2 minus pi over 2, which is equal to minus pi. So at omega equal to 1, the phase will be exactly equal to minus pi. In terms of amplitude, we can find out the value. So amplitude of L of j omega at omega equal to 1 is required for us. It will be equal to the amplitude of 1 over j times 1 plus j squared. And we kind of have it somewhere like we can also find out the imaginary and the real parts indeed. The imaginary part will be equal to 0 because we have the angle equal to pi. The real part of L of j omega will be what we are looking for. We can refer to this, or we can just find out the value from here, yeah, directly calculated here. But since we already have it, for the real part of L of j omega, when omega is equal to 1, we will have it as minus 2 over 1 minus 1 squared, which is 0, plus 4 times 1 squared. So this will be equal to minus 2 over 4 or minus 0.5. The amplitude is equal to the amplitude of L of j omega will be equal to 0.5, and the phase of L of j omega will be equal to minus pi. This is something that we are sure about right now. And the imaginary part of L of j omega as a result will be equal to 0. Okay, so at omega equal to 1, if I can show it to you, at omega equal to 1, we will be on the real axis and the amplitude will be minus 0.5. The value on the real axis. Then we need to check the situation when omega approaches plus infinity. As omega goes towards plus infinity, we need to see what happens to the amplitude and phase of L of j omega. Okay, so I will try to clean this part now because we don't need that. So we started at omega equal to 0 plus, we started at infinity with the phase of minus pi over 2 minus some epsilon. Okay, now I'm able to remove. At omega equal to 0, omega equal to 1, we will be at minus 0.5, which I would say is here. And as a result, the Nyquist diagram for that part will be like this. So we start at 0 plus, we approach the real axis as omega becomes equal to 1. And now we need to see what happens to the Nyquist plot as omega approaches infinity. You can see it over here, yeah? As omega increases, the amplitude will get smaller and smaller. At infinity, the amplitude will become equal to 0. And the phase at infinity will be equal to minus 3 pi over 2. So minus 3 pi over 2 will be here, but it will never go beyond minus or below minus 3 pi over 2. And as a result, I would say that the plot will be similar to this. Okay, let me keep it like that. So at infinity will be here. So that's what we have for segment number 1 in it, yeah? For segment number 2, we will get the mirror of what we have here with respect to the real axis. Because instead of having L of j omega for L of s, we will have L of minus j omega for L of s, and as a result, everything will be kind of mirrored with respect to the real axis. So this will be somehow the part of the Nyquist plot for segment number 2. For segment number 3, where we have S equal to RE to J theta, where R approaches infinity, let's see what we will have. Okay, I guess I will write it over here. So we have S equal to RE to J theta, where R goes towards infinity. L of S will be equal to 1 over RE to J theta times 1 plus RE to J theta squared. And R goes towards infinity. As R goes towards infinity, we can neglect the 1 that we have here. So this will be equal to 1 over R to the power of 3 E to J 3 theta. And R approaches infinity. And this will be mapped into a point that we have over here at the origin. So the point at the origin is the mapping of the L of S for the segment number 3. Now the most important part for this plot will be dealing with the segment number 4. In segment number 4, and I guess I will do it over here. For segment number 4, we have S equal to RE to J theta, where R goes towards 0. It's quite small. And theta goes from minus pi over 2 to plus pi over 2 in a counterclockwise way. Our L of S will be equal to 1 over RE to J theta times 1 plus RE to J theta squared. And since R goes towards 0, R is very small, we can now neglect RE to J theta, which is being added to 1. And therefore, L of S will be equal to 1 over R e to J theta. Okay, so we have kept only the pole at the origin. And R approaches 0. This could be rewritten in the form of L of S will be written in the form of R e to J alpha. Or we can alternatively write it in the form of R e to minus J theta, okay, to make it simpler. Now the capital R will approach infinity, and we know that theta goes from minus pi over 2 to pi over 2 in a counterclockwise way. So if I write this as R e to J alpha, now alpha is equal to minus theta. Since theta goes from minus pi over 2 to pi over 2 in a counterclockwise way, alpha will go from pi over 2 to minus pi over 2 in a clockwise way. Okay, so this is quite important. We'll have the clockwise changing of the phase from pi over 2 to minus pi over 2. And the angle and the amplitude that we have, or the radius that we have for the semicircle, will be infinity. So if I just draw this part of the Nyquist plot, and then I will add it to the rest of the plot that we have, we will start from pi over 2 with the angle with the radius of plus infinity in a clockwise way. We will approach the angle which is equal to minus pi over 2. So this will be the corresponding segment for this part of the segment of the Nyquist plot for this segment of the contour. Okay, so I can now come back to the main Nyquist plot that we have here. We were here, let's say at omega equal to 0 minus, and here we were at omega equal to 0 plus. And now to complete the Nyquist plot, we will have this part of the Nyquist plot, which corresponds to the small semicircle that we have in our contour. So this way, our Nyquist plot is complete, and we have the value over here as well, yeah, which is over here we have the exact value of minus 0.5. Now we can analyze the stability of the closed loop system by referring to this. We already know that P is equal to 0 because we had chosen this kind of contour to exclude the pole at the origin. P is equal to 0. Now we can take the point which is minus 1 over k and move it on the real axis. So for minus 1 over k, let me find some empty space to continue. Okay, I will do it here. For minus 1 over k, between minus infinity and minus 0.5, you can see that we have n equal to 0. So there are no encirclements of such a point, yeah? We have p equal to 0 as well, and as a result, z will be equal to 0. The closed loop system will be stable. For minus 1 over k, between minus 0.5 and 0. So any point over here, okay? How many encirclements do we have? We have one clockwise encirclement here, you can see it, and we have one big clockwise encirclement here. So n will be equal to 2. And since p is equal to 0, z will be equal to 2. And the closed loop system will be unstable with 2 unstable poles. For minus 1 over k between 0 and plus infinity, n will be equal to 1. If you take any point on the real axis on the right half plane, we have one encirclement around that point. P is equal to 0, so z will be equal to 1. And our system will be unstable with one unstable pole for the closed loop system. You can translate the conditions on minus 1 over k that we have here to conditions on k, and you will get exactly the same things that we had here. For k bigger than 2, our system will be unstable with 2 unstable poles. For k between 0 and 2, the system will be stable, and it corresponds to here. So basically, this is what we have for k between 0 and 2. And the rest could be also translated in a similar way. So in this way, we have indeed analyzed the stability of the closed loop system for this given example by drawing the Nyquist plot. And in this example, we had a pole at the origin. You should keep in mind that the contour that we have should not cross any pole of the system. If there is a pole on the imaginary axis, we should go around it, either include it or exclude it regarding the contour that we have. Alright, so I think that's all for this video. In the next video, we'll discuss about the stability margins. Thank you for watching and see you in the next video.